Professor Sezgin, you can start.
Okay, sounds good. Hi, everyone. Welcome to the webinar on rate-splitting multiple access in 2023. It's a particular honor to have as speaker Onur Dizdar, who is with Viavi Solutions in the UK. Let me just introduce, give a short introduction to Onur for those of you who don't know him. So Onur is a senior 6G research scientist at Viavi Marconi Labs in UK. He received his bachelor and master degrees in EE from Middle East Technical University in Ankara in 2008 and 2011 respectively, and his PhD in EE from Bilkent in Turkey in 2017. So both top universities, basically, and internationally well known. So from 2019 to 2022, he was a postdoc in the Communication and Signal Processing Group at Imperial College, London, in UK. And essentially, he has more than 50 years of research experience, both in academia and in industry. Therefore, I think it's going to be very interesting to have his perspective on RSMA. His research interests include wireless communications, channel coding, multiple access techniques, multiple antenna communications, signal processing, and machine learning. So quite wide, as you can see. So before I hand over to Onur, let me just briefly mention the rules. So when Onur is going to start, basically you are going to be muted. You are going to be asked to type your questions in the chat. And once we enter the Q&A session, basically, which is going to be 10 minutes, then either you can raise your hand, and then you will have the chance, basically, to ask your questions, or we are going to choose question, and we are going to choose the questions which have been already addressed in the chat. Okay? Then I would hand over to Onur. Onur, please.
Let me share my screen first. Can you see my screen?
Yes.
Okay. Thank you very much, Professor Sezgin, for this kind introduction and also inviting me to talk here on this RSMA webinar series, which is by IEEE Communication Society, and also special thanks to all the organizers. Hi to everyone attending this presentation. My name is Onur Dizdar, and I work as a senior 6G research scientist at Viavi Marconi Labs. And my talk today is on the low complexity designs for RSMA for practical applications. As you know, we are now on this way to standardization of 5.5G and also even for 6G. And I'm going to try to give some discussions and insights and the designs that we do to make RSMA more suitable for practical applications and potentially make into the standard. So this is the outline of my presentation. I will start with a brief background and motivation. Then I will move to low complexity system designs for RSMA. I will give a system model and designs for two different scenarios. And finally, I will give some discussions on the opportunities and challenges on the way to 6G. So let me start with the background information. So multiple access has been the fundamental pillar of the wireless communication standards since the day one. And from 1G to 4G, we have tried to allocate users in the network using different frequencies, time slots, or codes, or both frequency and time with fine resolutions to try to serve them with the system that we design. So from FDMA to TDMA to CDMA to OFDMA, from 1G to 4G, we have managed to serve users with a point, with a single point, and we have been trying to achieve what we can get with these, using these schemes. From 5G, and with the additional dimension that is added using the multiple antennas and the increased number of multiple antennas, we now have a additional domain that we can add users. I mean, multiple antennas have been also in 4G as well, but the increased number of antennas has led us to the idea that we can make an efficient use of these antennas to allocate more users in the network. So SDMA, or multi-user MIMO, has shown with the 5G, and what we can do with SDMA is we can serve multiple users at the same time and frequency resources by assigning separate beams towards each user. And SDMA can achieve a high data rate when we have the actual imperfect knowledge of the user's channels or the user's directions, so that we can form beams towards each user, and we can avoid interfering their data between the users, and so that we can achieve a reliable communication and higher data rates. So here the critical point is to obtain the information of the channel of each user in the network. So in practice, this is a challenging task. So in 5G, we have several methods to obtain these channel metrics, either by sounding signals back at the base station for estimation, or by performing some feedback from the users to the base station, so that we can have a knowledge. But as you can imagine, we can never achieve a perfect knowledge of the user channels at the base stations in practice. So in that case, a drawback of SDMA or multi-user MIMO is that it has a performance degradation, because the imperfect CSIT or imperfect channel knowledge of the users at the transmitter causes an imperfection in the beams that we form. So that means the beams that we form actually can interfere with other users. So the data from one user can affect the signal to the other user, which actually degrades the performance because the multi-user interference can become a dominant compared to noise, and this limits the throughput that we can give to users. And this is actually a valid problem currently in 5G, and it's difficult to operate multi-user MIMO or SDMA. So with this knowledge, researchers have looked for other candidates to improve the performance of multi-user MIMO in these kind of situations. So one of the schemes that is proposed is multi-user NOMA. So NOMA for single antenna broadcast channels. So what it does is you allocate the data for multiple users on the same time and frequency resources and spread them in the power domain. In the multi-antenna scenarios, what can happen is users are grouped into groups that have multiple users, and then wide beams are used to serve each group, and the data for each user is embedded in this wide signal. So the signal and the data for each user is embedded using a superposition coding in this larger beams. And at each receiver side, we perform some kind of interference cancellation called successive interference cancellation to extract the data that is intended for each user. So NOMA has been shown to be useful in some scenarios. For example, when the users are aligned spatially and they have different distances to the base station in general. But also theoretical research has shown that NOMA, multi-user, multi-antenna NOMA is actually not very useful except for several special scenarios compared to SDMA. And we also need extra processing at the receiver side. So the complexity of this processing increases with the number of users, which is something that is not really desired in practical systems. So these drawbacks of NOMA also make it challenging to compete with space division multiple access. Another multiple access scheme has emerged called rate splitting multiple access. And in rate splitting multiple access, the multiple users are served using separate and combined RF beams. And the figure illustrates some of this. So we can say that RSMA generalizes multi-user MIMO and NOMA. And it can achieve a high data rate with perfect and imperfect channel state knowledge at the transmitter. So these advantages of RSMA has made it a solid candidate to enhance SDMA in practical systems, but it also has some drawbacks, including a extra processing for successive interference cancellation at the receivers. So although this complexity of it does not scale with the number of served users, it is still a concern in practical applications. So before going into the details, let's go back to some basics and try to understand why rate splitting is a good option to enhance multi-user MIMO. So the rate splitting has also its roots in information theory, and it has stemmed, the idea stemmed from the single antenna interference channel model that is investigated in information theory many years ago. And in this channel model, we have two pairs of communicating nodes that two transmitters want to transmit data to two receivers, but their signals transmitted from one transmitter also is received at the other receiver, which causes an interference. So in this type of channel problem, the capacity region has not been characterized even to date. So although it looks simple, it's not actually a simple problem to understand what should be done and what's the capacity region that can be achieved in such a channel. And the proposed strategies with point-to-point transmission codes at the transmitter and the decoding the interference or treating the interference as noise at the receiver covers some of the scenarios, but not all of them. So depending on the interference levels, these strategies are not the best that we can do to perform good in these type of channels. So the seminal work from Hangobayashi, which the rate splitting is used for the first time, achieves the largest achievable rate region for the interference channel. And it can be shown to be asymptotically optimal at the high SNR regime and interference limited scenarios. So although the capacity region is not known, we know that Hangobayashi scheme can have is the best thing we have so far, and it's also optimal at some interference limited scenarios. So this interference limited scenario is a keyword that we will use. So to define interference limited regime, it is the interference from one link has more impact on the performance of the other link than the noise added in this link. So for example, the interference from transmitter 1 has more dominant than the noise at the receiver 2. So that means that our performance can be as good as the interference level transmitted from here. Moving to multi-antenna systems, we have another information theoretic channel, which is the MIMO broadcast channel. So our aim, like we do in 5G, we have a single point transmitter, and we want to serve multiple users over the multi-antenna channel. And word-to-paper coding, it is a nonlinear precoding scheme, can achieve the capacity region if we have the perfect channel state information at the transmitter. So if we know H1 and H2 perfectly at the transmitter, then we can achieve the capacity region with this word-to-paper coding. But again, this scheme is not very practical, so it cannot be used in practical systems. So we go again a search for a low complexity method, which is a linear precoding and zero forcing beamforming, which has been shown to achieve the optimal degree of freedom, and again with perfect CSIT. So this is like a SDMA or multi-user MIMO scenario that we discussed in 5G. So here the critical number of interference-free data streams that can be supported in a single channel use at high SNR regime. So again, this is a terminology that we will use in the following slides. So again, you can see that if we have perfect CSIT, then we know what to do. And it is clear that the strategy should be the pre-coding depending on the channel state information. But as we mentioned, this is not the case in practical systems. So when we have imperfect channel state information, then this MIMO BC channel starts to become like a MIMO IC or MIMO interference channel. So we have now interference from the data stream transmitted to that user, also appearing on that user. So under that circumstances, the straightforward thinking is that then we need a Han-Kobayashi-like scheme to use under such circumstances. And this is where the RSMA comes into play. So let's look at the RSMA, the basics of RSMA over a two-user example. So this explanation is over a more abstract definition of messages. So let's assume we have two messages that are intended for two receivers from a multi-antenna transmitter. So what happens in multi-user MIMO that we encode them and modulate them, and we apply linear precoding to each message, and we transmit over the air. But in rate splitting, what we do is we actually split these messages into two parts. From W1, we obtain WC1 and WP1. And again, from W2, we obtain WC2 and WP2. So after the splitting, we combine a portion of these messages into a new message. So we call these combined messages as the common parts, and the obtained message as a super common message, or a common message in short. And the other parts that are split from the original messages are the private parts. So what happens is this new message and the remaining private messages are separately encoded, modulated, and linearly precoded before getting transmitted into the air. And at the receiver side, what we do is we first decode the common stream without considering the interference from the other private streams. And then we extract the estimation of the common message, and then extract the related part to our receiver, WC1 or WC2. And after the reconstruction of the original common message and subtraction, then we move to decode the private message for each user and extract the related message. while treating the private message of the other user as noise. And then we combine these messages to obtain our final message. From a more practical perspective, we can look into these messages as bit streams. So what happens in rate splitting is that these bit streams are divided into two parts, the common part and the private part. So this division, it does not matter how it happens if we are considering a generic system. So over in this example, we just divide from the beginning, and then we have a message combiner here to combine the bits. And the usual blocks in the transmitter chain, channel encoder, interleaver or modulator, and linear precoder are applied to all these three streams. And then the signal transmitted over the air is received at each receiver, and each receiver first aims to decode this common message using the receiver chain and obtains the original, formed common message first, and then gets the related part and extracts it. And after the signal construction, again, the receiver chain is operated, and then the private part is extracted and then combined into the final bit stream. So let's move to the motivation of our presentation today, which is the low complexity designs. So the designs that I've explained so far is also highly dependent on using the optimal precoders and the power allocation between the common and private streams. So we need to find the optimal point to achieve the maximum gain that we can carefully. We may not get the best performance, and we may not even suppress the performance of multi-user MIMO or SDMA. So we need to carefully design the precoders and power allocations. And there are numerous works in literature that worked on this thing under different scenarios and under different system models. But the thing is, the complexity is high in most of these existing algorithms for the system design, because it's not a straightforward task to design the precoders and the power allocation. And what we generally do is we write optimization problems, and then these optimization problems are in a complicated form. So generally what we do is we use computer-aided solutions to get the optimal precoders and power allocation metrics. So the drawback is these cannot be implemented in real time or in real systems. So there is, in real systems, there is a limited computation power, although it's very high in these days. Still, operating these algorithms at the base stations and with a very, very small latency is not possible. So this makes it difficult to design systems and also analyze the performance, especially for large number of antennas and or users. So this is also a critical point, because nowadays in 5G we have more than 32 or 64 or even 200 antennas, and this is expected to increase in 6G. So we need to understand how systems behave with such large number of antennas and design optimal systems for these kind of requirements, which is difficult to achieve with these kind of computer-aided designs, because the computation of the CPUs or GPUs are limited anyway. So this gives the motivation to actually look for practical algorithms that give close to optimal performance and to design these systems or analyze system performance for wireless communication standards. So these include, and not limited to, practical precoding, practical rate, power and resource allocation, receiver designs, and signaling designs, etc. And our aim in this work is to design a practical rate, power, and resource allocation scheme using existing practical precoders that are used as benchmark in practical system designs so far. And we covered the underloaded and overloaded scenarios in multi-antenna networks, which I will define in just a moment. So let me move into the low complexity system designs for RSMA, and let me start with the system model. So we consider a transmitter serving multiple users in the downlink using n number of transmit antennas. And number of users in the system is denoted by K. And we use the index K to define the set of user indexes. And we assume that each user in the system is a single antenna receiver. And the base station has a total power of P, and we assume that the precoders and the symbols are normalized to unit power in our system design. So our system can be underloaded, which means that the number of so in many scenarios in cellular systems, this could be a valid assumption. But nowadays, with the introduction of IoT and a large number of devices now connected to the networks, we may also encounter overloaded scenarios, so that the number of transmit antennas is actually smaller than the number of users in the cell. So you can imagine this can also happen in crowded areas like stadiums or gatherings, etc. So these scenarios are now faced more and more frequently, and we need to come up with designs for these systems as well. So we will benefit from the DOF analysis for the RSMA to design our systems in these underloaded and overloaded assumptions. So as you can, you may remember, DOF, or the number of interference-free streams that can be achieved using RSMA, is an important metric that gives us some hints to design, to how to design the communication scheme using the RSMA. So you can see we can investigate this DOF in perfect and imperfect CSIT assumptions, and we can target different metrics using the total DOF, maximizing the total DOF, or maximizing the minimum DOF achieved overall users. So each of these metrics lead to different system designs, and we can choose them based on our requirements for our system. So sum DOF, or maximizing the sum DOF in perfect CSIT means we use zero forcing beamforming for the minimum number of antennas or users, depending on the number of antennas. If our number of antennas is larger than the number of users, so we have zero forcing beamforming for K users over the private streams, and we don't need any common stream. So you can notice this is actually the multi-user MIMO scheme that we mentioned. So in that case, we don't use RSMA, and RSMA boils down to just the multi-user MIMO. But the imperfect CSIT case is different. So in that case, we have zero forcing beamforming for the private streams, but we also need a common stream to split the rates and achieve a higher sum DOF under the case of imperfect CSIT, where the DOF of SDMA just saturates. So for the maximum fairness DOF, this actually targets to maximize the minimum rate that a user can get in a network. So in that case, we can just investigate these designs to achieve this maximum fairness DOF in two parts, for the underloaded scenario and overloaded scenario. And in the underloaded scenario, again, we have ZF forcing beamforming for K private streams and an additional pre-coding for common stream in the imperfect CSIT case. But when we come to the overloaded scenario, the scheme becomes a little bit more complicated. So we need to separate the users into two groups of n users, one group containing n users and the other group containing k minus n users. And we serve one group including n users using the private streams, and the other users in the other group are serve the common stream. And we again can use zero forcing for the private and random pre-coding for the common. In the imperfect CSIT case, again, we have two groups, and the users in one group are served using private and common, and the other users are served on the common. So these designs in the DOF analysis gives us a hint on what to do in a practical system. But we need to allocate the optimal power to actually achieve gains in these kind of systems, which the DOF analysis does not tell us how to do. We don't have any explicit expression on how to allocate the rates and powers between the private streams and the common streams and the groups that are served in the overloaded scenario. So we search for these kind of optimal power allocation schemes with low complexity. So let me start with the underloaded scenario. So I will try to skip the technical details here and just to give you the basic idea. And for more details, you can refer to this reference. And if you are really interested in the technical details. So in the underloaded scenario, we say that the number of transmit antennas is larger than the number of users. And we consider a channel model in this scenario, which models the error due to mobility. Although this work can be generalized to a general channel estimation error as other channel estimation imperfect CSIT scenarios, in this particular work, we consider a estimation error due to mobility. So how do we model this? We have our channel for user K at the time instance M. So the time that we will perform a transmission to multiple users. And this channel is related with the channel of user K at time instance M-1. And this also is the CSIT that we have at the transmitter. So what this means is, in a mobile system, we have a channel state information, the channel knowledge of the users at the transmitter side. But since this feedback from the users to the base station takes some time, until the time that we send the feedback and we process it at the transmitter, there has been a change in the user's channels due to the mobility. So by the time we are ready for transmission, we calculate our precoders over this CSIT for the transmission. The instantaneous channels of the users have changed since they've just moved around. So to model this, we add a error to imitate the change in the channel of user K. And the actual channel and the CSIT is related with a coefficient epsilon, which depends on the Doppler shifts in the system resulting from the mobility of the users and the CSIT update delay in the network. So the time that takes us to send the feedback from the users to the transmitter side. And the RSMA signal at transmitter is written in terms of the private streams pre-coded using a ZF precoder for private streams, calculated using the old channel state information. And we also have the random precoder for the common stream and pre-coding the common stream that we create for the users. And we have a power splitting ratio T that distributes the total power between this common precoder and the private precoders. And you can note that we also distribute the power equally among the private precoders, so to make it a low complexity scheme. So this is also a commonly used assumption industry, just to make things simpler. And you can also note that when T is equal to 1, the common stream is turned off and we have the multi-user MIMO. So our design can boil down to multi-user MIMO or SDMA if we have a, for example, perfect CSIT case. So the RSMA signal at receiver K can be written by the transmit signal passing through the time and the additive white Gaussian noise. And the ergodic achievable rates at each receiver can be written by these expressions. So I won't go into the details, but you can see the interference from other users in the private stream and interference from the all private streams in the common stream is in the denominator. So this affects the power allocation coefficient that we need to design. And how we will design this is we write the sum rate problem and we find the T to maximize this problem. So our problem is find the optimal power allocation that maximizes the sum ergodic rate. So this can normally be written as a optimization problem, and we can use some kind of simplifications to make this problem easily solvable by computer-aided algorithms. But here we take another route and we use some statistical properties of the terms in the numerator and the denominator of the achievable rates. And we do some algebraic manipulations and assumptions, which I will not go into the details and not bore you, to come up with a upper bound, a lower bound for the sum rates. And to make this simpler and to capture the behavior at the interference limited regime that we mentioned before, we make the highest NR assumption just to make the power allocated to the private streams going to infinity. We come up with a simpler expression for the lower bound for the sum rate maximization. And we then simply take the derivative with respect to T, and we come up with a concise expression for the optimal power allocation that we need to do to achieve the highest gain possible. So this power allocation coefficient is in closed form, and although it looks like it's not still really pretty, it can be calculated in real time, either by storing possible values into the memory or by just performing these analytical operations in CPUs or GPUs nowadays. So as you can see, the optimal power allocation depends on the number of users in the network and the CSIT quality that we have, so that we can make sure we get the best that we can get using RSMA. So let's look at some simulation results to see if the coefficient that we derived actually works. So here we consider different deployments, number of users and number of transmit antennas, and different user speeds. And we are trying to understand if the SDMA performance, if the RSMA performance actually performs better than SDMA. And for comparison, we use exhaustive search to find the optimal power allocation coefficient, so that in this system design that we have, instead of using the closed form solution, if we search for all possible values of T, which is not very practical again, but it ensures that we get the best that we can get from this system design. And we compare it with the closed form solution that we proposed just to see how good we are. And we can see that for the different scenarios, the proposed scheme actually performs close to the exhaustive search. So it means that without the requirement to do any kind of exhaustive search or computer-aided algorithms, we can achieve a decent performance, and we can suppress the performance of STMA for different scenarios. So we move to the comparisons using the sum rate and also throughput performance. So here in this figure, we investigate the sum rate performance obtained using the RSMA using the closed form solution that we had for the power allocation, and RSMA using the exhaustive search that we find the optimal power allocation using this method. And we compare the performance with STMA for different user speeds. So for the performance of STMA, you can see that starting from the low user speeds, as we increase the speed, the performance tends to drop. And even though we increase the SNR from 25 dB to 35 dB, there is a saturation here. So because this is the result of the effect of mobility, so even though we increase our power, the quality of the CSIT does not improve, because the quality is not actually depending on the SNR, but the user speeds. So increasing the power or increasing the quality of channel estimates does not help us in this case. And that's why the CSIT actually puts us into the interference limited regime. We can achieve a good performance with RSMA. And here, the performance with RSMA with different SNR values are shown. And you can see the saturating performance of the STMA is actually not seen here. And as we increase the power, we can achieve a higher sum rate with RSMA. And we also show a throughput performance using a link level simulation. And again, the gain is significant. So this results for 32 transmit antennas and 8 users. We can conclude that RSMA achieves a significantly higher sum rate compared to STMA and has a non-saturating performance with respect to SNR. This proposed closed form power allocation coefficient in a multi-antenna receiver setup. So although we didn't consider the multiple antennas at the receiver side, we can still try and see how it works out for us if we have multiple antennas at the receiver side as well. So you can see here the comparison between STMA and RSMA. The throughput is also significantly larger for the RSMA. And you can see there is a drop in throughput and then an increase as a non-monotonic behavior for the RSMA. This is due to our assumptions that we have single antenna, multiple antennas in this case. So here we investigate this scenario where we have 2 streams per user and 3 streams per user, with the users having 4 receive antennas. And we can conclude that with this power allocation scheme, the gain is even more significant with multi-antenna receivers and multiple streams. So using simple ZF beamformers and a simple calculation for the power allocation, we can actually suppress the performance of STMA when we have mobility. But our assumption is we have the number of antennas larger than the number of users. So let's move to the case where we have an overloaded scenario then. where we have the number of transmit antennas is smaller than the number of users. So again, this bit is based on a reference that is published and open to public access. So I will not go into much technical details, but if you're interested, you can refer to the reference. So here in the model, so HK denoting the channel of user K, and the CSIT for user K is denoted by H hat K. And again, they are correlated by a coefficient epsilon. But here we don't consider any specific mobility assumption. We just consider a general epsilon. And we also have the CSIT imperfection in the form of an additive noise term. And in this system design, we also consider the channel disparity between users. So to model the path loss or the distance, we also add another coefficient between 0 and 1 to the channel model. So in this scenario, what we have is we have the transmit signal again, similar to the previous case. We have the common stream, we have the private stream using ZF precoders, and we have the power allocation ratio for the private streams mu k. And we also have another coefficient t here again, and that we will try to find. And the RSMA signal at each receiver is now formulated by the channel multiplied by the disparity coefficient. And the ergodic achievable rates are the expectations of the logarithms of the SANRs. So what we have is a maximum fairness problem in this case, because we want to serve all users. We don't want to exclude any user. And in order to achieve this, we cannot maximize the sum rate, which will exclude some of the users and choose the best users to serve. So we formulate a maximum fairness problem for each user, adding the private rates and the portion of the common rate that is allocated to a specific user. And we find the minimum among the users that we can serve with the smallest rates, and our aim is to maximize this by finding the optimal precoders and rate and power allocations. However, the system design and the solution is more complicated in this case compared to the sum rate maximization. And one of the reasons is form two groups, and one group will be served by zero forcing precoding at high SNR, and some users will be served by the common stream. So we have separate rate expressions for users. And we know that we have more users than the number of antennas. So the interference, we expect it to be high. So we can assume that the common stream may be required at all SNR regimes. So we cannot benefit from the high SNR assumptions to simplify our expressions. And we don't know if the design with ZF precoders will perform well at low SNR too. So we need to just make sure we achieve the best with the low complexity precoders. So we actually have two separate system designs with ZF precoder and maximum ratio transmission precoding to cover all the scenarios from low SNR to high SNR. So because we know that MRT precoding is optimal at the noise limited regime and zero forcing is optimal at the interference limited regime. So we formulate our problem between the maximum rate between the using the zero forcing precoders and the MRT precoders. And for the case of MRT precoding, we serve all users directly over the private streams using the using MRT precoding. And we assume that we allocate the power equally among the MRT precoders. And defining the K as the user that has index of the user that has the minimum disparity, channel disparity, we define the achievable rates as you see here, and our problem formulation is the maximization of this achievable sum of these achievable rates for the user that has the minimum channel disparity. And lots of algebra lower bounds, and we, for different assumptions, high SNR and low SNR assumptions, and we take the derivative with respect to t and equate it to 0, as we did for the underloaded case. For the ZF precoding, we have two user groups, group 1 and group 2, including n users and k minus n users. And we have no common user in any of these groups, so users are completely separated. And ZF precoding is designed to null the intra-group interference in this group 1 among the n users. Again, we define the k tilde as the index of the user having the minimum disparity in this group, and assuming equal power allocation for simplicity, we have the achievable rate expressions here. Skipping the details, we have a problem formulation here that we need to choose the rates in one group served only using the common stream, and the users in the other group are served by private and common streams. So a proposition says that in order to achieve the maximum fairness, we need to equate the rates that are the user rates that are in the two groups. So using this proposition, we solve for t and beta, and we just first solve for the t first, check if this condition is satisfied, substitute into the expressions again, solve for beta, etc., etc. So it's not easy to tackle, and we have lots of simplifications under various assumptions to capture different scenarios. So again, I'll not go into the details, so you can check the reference for details if you're interested, but I will not present them because it's just not pretty. But the final solution is we have the closed form solutions for the achievable rates, and we calculate 5 achievable rates for the perfect CSIT case and 6 achievable rates for the imperfect CSIT case using closed form solutions, and we choose the maximum of them. And depending on that index, we choose whether we will apply ZF precoding or MRT precoding, and we have also expressions for the optimal power allocation and rate allocation between the groups in each between the users in each group. So this is an example for the derived expressions, and I will not explain them, don't worry, but it's just to give you an idea. Although they don't look pretty, they can actually be implemented easily and calculated in real time because they include very simple logarithmic and addition and subtraction operations. So let's move to the results directly. So we have the simulation results, and first we wonder if this design actually can compete with the computer-aided solutions. So for this case, we consider a system with 2 transmit antennas and 4 users, and we use this paper as the benchmark scheme, which uses a computer-aided algorithm to calculate the precoders and the power allocations and the rate allocations. And as you can see, for different levels, achieve a close performance to the optimal algorithm that uses computer-aided methods. So, and we compare the runtime on a CPU that we have, and we can calculate the power allocation and rate allocation coefficients in this figure in 0.1 seconds, while it takes like almost 3,000 seconds to calculate with the computer-aided algorithm. So we can say that this is good enough for a practical design, and we can use this method to investigate the performance of under different assumptions, and also with large number of antennas and users, which we cannot achieve with the computer-aided algorithms, so that we can target next generation standards and understand how we will perform with increased number of transmit antennas. We also compare the proposed method with the exhaustive search as we did in the underloaded scenario. And for that exhaustive search, we use the design with zero forcing precoding and MRT precoding for different system designs, system parameters. For example, 4 antennas and 8 users, or 8 users, 8 antennas and 16 users. And we distribute randomly the disparities of users. So each user, different users may have different distances to the base station. And you can see zero forcing, design with zero forcing, and design with MRT precoding perform good in different regions, and rate allocation for each case. And with our proposed method, we can actually track the optimal performance in a close distance, so that we can switch between zero forcing and MRT precoding for in different SNR regions. For large enough number of antennas, you can see still the designs change in the different SNR regions, zero forcing or MRT precoding. We can switch with the proposed algorithm. And now we can safely move to obtaining more simulation results and see how we can perform with RSMA in overloaded scenarios. So this scenario is 4 transmit antennas and 8 receivers in a system, and imperfect CSIT with varying levels of CSIT quality. And we compare with 2 benchmark schemes. One is SDMA with MRT precoding. So all users are served directly by using MRT precoding, and also SDMA with zero forcing precoding and grouping. So in that case, users are divided into K/N groups. And in each group, we use zero forcing precoding to null the intergroup interference. So you can see from the figures, the RSMA with the proposed method outperforms significantly the benchmark schemes. So even though we use zero forcing or MRT precoding, we are limited by the interference due to the number of users being larger than the number of transmit antennas. So the saturating performance of SDMA can be overcome by using the RSMA by either zero forcing and MRT precoding. In another scenario, we consider 8 transmit antennas and 24 users. So in this case, again, with perfect CSIT and different levels of imperfections, we can achieve a higher maximum fairness rate compared to SDMA and the saturating performance of SDMA-based benchmark schemes. Now we increase the number of transmit antennas even further for 32 antennas and 40 users, which is very challenging to analyze with computer-aided designs. We can still see that for different levels of CSIT imperfections, we can achieve gains using RSMA. So we can conclude that RSMA outperforms the benchmark schemes when we use the proposed low complexity system design. So a common question that comes into mind and asked is, okay, if we have an overloaded scenario, we have more users than the number of transmit antennas, then we can use scheduling to
Onur,
schedule users in orthogonal time slots.
Onur, may I
Yes.
interrupt you here? We are past the 1 hour mark.
Okay.
Yeah, just to let you know.
Okay, sorry.
No worries.
So just then now conclude this part and then go into the standard discussions. So even with, if we use scheduling in multi-user MIMO, the proposed method can outperform the multi-user MIMO with scheduling, so that even though in the current designs and the current considerations in the current 5G system, we can actually use RSMA to suppress the performance of the existing multi-user MIMO under below particular CSIT qualities. So without any further comments on this, I will go into the opportunities and challenges on the way to 6G. So in the technology in the current considered for the 6G or beyond 5G, we can say that a technology can make into the standard if it addresses the requirements of the new standard, a significant use case or service in the new standard, or it enhances a technology or service in the existing standard, or solves a problem of the existing standard. So all of these can be a valid reason for a technology to be considered to make into the standard. But we also need to have it being implementable and performing similar to or better than the other candidates considered with that, and has interplay with other schemes and enabling technologies in the standard, and attracts interest from several companies, which is also like a major requirement for the technology to be considered. So recently, Viavi has made a proposal to release 19 to consider rate splitting multiple access as a study item. So the question is, how can RSMA make into 6G or even beyond 0.5 beyond 5G? So Viavi's proposal was to target the problems of SDMA, which could be due to user mobility, as we just presented, because user mobility is still a problem in 5G, and with the introduction of UAVs into the network or high altitude platforms, this will be a even more problem. So in order to make SDMA work, we need to enhance it. So user mobility is one of the aspects that we can promote RSMA. Another one is the spatial separation of users. So if the user separation in space domain is not enough, then multi-user MIMO has a problem serving these users. So RSMA can also be used to target that. And another important problem is CSI feedback overhead. So the current overhead due to type 2 CSI feedback is large. So what this means is that we spend so much resource to just to pass the CSI information from users to the transmitter. This affects our system performance. So the discussions currently in 3GPP and is to how to compress the CSI feedback so that the overhead can be reduced. And companies have proposed machine learning methods for this compression, but it's still, there is no consensus on how to accomplish this. So this could be a good motivation for companies to consider RSMA. We can also use RSMA to enhance the performance SDMA to support services like joint unicast and multicast or side link. So another proposal from BBC has highlighted this enhancements for joint unicast and multicast, so that we can perform a multicast to multiple users and also do the unicast jointly using RSMA by doing the multicast over the common stream and unicast over the private streams, etc. And also side link, which is like a challenging service because, again, the channel state information that is served directly from one cell phone to the other one is not doesn't have good quality. So we can employ RSMA to serve the side link service as well. Address new use cases, services, or technologies, and make RSMA like the best option to realize these use cases or services, such as sensing or perceptive networks, non-terrestrial communications on new frequency bands, especially in terahertz and centimeter wave, or FR3 as 3GPP calls it. So there are problems occurring due to the large antenna arrays. So the antenna arrays can become so large that they can be
Onur,
partially blocked by buildings and partially satisfy line of sight. So these kind of channel conditions need to be understood. Hello.
yeah, you are audible. For a second, the connection was
Okay, sorry.
weak. Yeah, the connection was weak for a second, but you are audible now.
Sorry, thank you. So these new conditions need to be investigated by 3GPP as well. And RSMA has also potential to address these new challenges with large antenna arrays and in new frequency bands, and also maybe target new use cases that could be potentially killer applications like XR, AR, or virtual reality. So all of these things can be need to be addressed by in real time with significant gains to make companies interested in RSMA. So these need to be shown in real time, but still employing RSMA as an enhancement to SDMA still requires changes in the network and the transmitter and receiver design. So these need to be justified with the significant gains so that people go into the trouble to implement these things. So here comes some practical concerns, like the error propagation in SIC due to imperfect CSI at the receiver side, or efficient. We have an additional stream and we need to make channel estimations for the stream to receive it. We need to justify the additional resource that we will use to send pilots for the stream, or we need to come up with efficient ways to design pilots so we don't increase the overhead just because we are sending this additional common stream. And we need to come up with signal and protocol design so we can notify the users that we are using a common stream and what portion of the common stream is allocated for their use, etc. So these things need to be addressed before the other companies become interested in actually looking into these things. and also some research topics for low complexity designs, like the SIC-free receiver design, which can be used to address the error propagation due to imperfect channel state information in the receiver side, or the hybrid IRQ design for RSMA, because some of the designs like hybrid IRQ are considered regardless of their technology. So companies will not give up on some of the technologies that are used, like hybrid IRQ. So we need to ensure RSMA works with existing techniques, and so that the companies are more comfortable in accepting these kind of new technologies. And also, we need to integrate with other candidate enabling technologies with low complexity algorithms like integrated sensing and communications, semantic communications, X-large MIMO, and reconfigurable intelligent surfaces. So we need to prove that RSMA can work with these easily with gains that can justify its introduction. Thank you for your patience, and I apologize for the overtime. Again, special thanks to the organizers. And that's all. Thank you very much for listening.
Thank you very much, Onur. And this was a very engaging talk. Indeed, we got a perspective vis-a-vis practical implementation of RSMA and the constraints. This was very informative, and I'm sure the audience would have learned a lot from this presentation. We'll move to the question round, and we have Abid Arif who wants to ask a question. You can unmute yourself and ask this question.
Do you have my voice?
Yes,
Hello.
I do. Hello.
Thank you for your organization, and thank you for your nice presentation, Onur.
Thank you very much.
I enjoyed from your presentation indeed. I have just some questions related to your optimization problem. Let me ask the question one by one. My first question is that, is your optimization problem an unconstrained optimization problem or constrained optimization problem? Because in your slide, I didn't see anything related to constraint, for example, the quality of service, the power which is used by each user, and so on.
So yeah, here I did not go into the details, unfortunately, so maybe this is not very clear here. So we express this as a actually a constraint, obviously, of course, a problem. Like in our system model that I presented, we have it, for example, a total transmit power. So this constitutes one of the constraints, for example. And for the quality of service, here in some rate optimization for the underloaded scenario, we don't consider that a quality of service. So here, this is ensured by using zero forcing precoder and equal power allocation over all users, so that each user can get a portion of the rate supplied by the private streams. But the question comes how much we give to the private streams and how much we give to the common stream. But in the simplifications, this is ensured. For the max-min problem for the overloaded scenario, again, we don't specify here, but when we use the precoders or the transmit signal in this form, we ensure that some rate is allocated to the private stream, some rate is allocated to the common stream. And since this is a maximum problem, we try to guarantee that the minimum rate is larger than zero anyway. So this is like a quality of service constraint on its own. So although by simplifications, we make it look like a unconstrained problem, the constraints are actually applied in the expressions that we give, like the zero forcing precoding and total power allocation and the power distribution, etc.
Okay.
Hopefully I could answer your question.
My second question is related to the quality of service indeed, because in RSMA, our strategy is to splitting the rate of the users to provide a reliable communication over each link. Okay.
Mm-hmm.
As you know, when one of the link is constrained to have a short packet communication, for example, you said the application of your work for Internet of Things. In Internet of Things, at the edge layer, we have this constraint, and the short packet communication is really one of the main constraints. To quality of service constraint be assumed, I think using the classical channels capacity formula is not a suitable formula to be utilized in formulation of the problem.
Mm-hmm.
In this case, I'm suggesting you the practical formula first presented by Professor Vincent Pugh, in which you are considering the state of the channel, and that formula can be used in your problem. But as you are incorporating the parameter t in your problems, these problems are online optimization problems, and in practice we need some such problems. But about the solution strategy of your problem, you didn't say anything about the convexity of your problem. Is your problem, for example, in this slide, over the time interval from 0 to 1, is your objective function always convex? Are you sure about this?
So in this formulation, for example, like we spread, for example, this problem into two parts, the MRT precoding and the ZF precoding. For the MRT precoding part, what we do is we actually write these expressions and we take a derivative with respect to t. So hoping that in the valid interval of t, like between 0 and 1, these things are convex problems. So we don't check the convexity, but we check it like to see if this is actually a convex problem by numerical results. But in the ZF precoding part, the problem is a little bit different. So in this proposition, we say that the problem is actually trying to solve these two rates in each group, whether they need to be equal to each other. So in that case, we don't care about convexity. We just try to find the optimal power allocation and rate allocation, for example, that makes these two expressions equal to each other. So in that case,
how do you find the optimal solution?
I mean, when we equate these things, I didn't give the details here, but these rates actually have some kind of simplified forms. Like, for example, you can see here for the MRT, we have similar expressions for the ZF precoding part. And we just say that, okay, this rate should be equal to another expression. And then we try to solve these expressions for given for optimal t and beta. So maybe I should have provided some analytical expressions here, but I was scared to bore people, so I skipped those parts. But you can check this reference for detail, and also maybe if you like, we can have a offline discussion about this on how to do this. So that's basically how we try to do it.
Okay, thank you for your answer. Actually, in online problems, to find the optimal solution, I suggest you to go through the machine learning and employing the reinforcement learning in such problems. And you can use your closed forms to find the best initial fitting for those online problems. For example, if you are going to use reinforcement learning, you need some initial points. And to get a better convergence speed, you can use this offline solution for your problems. Because by increasing the number of users and the number of antennas, the complexity of solution actually increases. And in such problems, I suggest you to go through the machine learning to find the optimal solution. Thank you for your answer. Another question is related to the power allocation strategy that you have obtained through the closed form.
Yeah.
How do you allocate the power in a nutshell among the user? How do you allocate the power among the user? For example, in time frequency domain, for the OFDM case, we are using waterfalling. And the more power is allocated to those users having reached a situation from the signal to noise ratio point of view. But here, I'm going to give you some insights as you talk about 6G application. In delay Doppler domain, the power allocation strategy is completely different from the time frequency domain. Similar to the non-orthogonal multiple axis, in delay Doppler domain and delay sequency domain, and also in delay scale domain, these domains are domains that I'm focusing on them currently. The power allocation strategy in these new waveform domains is something similar to non-orthogonal multiple axis. In NOMA, as you know, we allocate more power to those users having poor channel state from the signal to noise ratio point of view. How do you allocate power among the users in this problem? Are you allocating more power to the poor users or to the rich users?
For private streams among the users, we consider like the equal power allocation.
Sorry, do you know why I asked this question? Because in your presentation, I didn't see any simulation results in terms of, for example, power allocated to each user with respect to the user situation, the user signal to noise ratio situation.
Yeah, so that's let me see here. Okay, so this is how we do it, like equal power allocation for simplicity. So this is our assumption because this is currently what is done in most of the practical systems due to its simplicity. But again, as you mentioned, the delay Doppler domain with the new waveforms, like maybe OTFS,
yes,
and the use of OTFS with rate splitting, new power allocation methods could be investigated. So in this work, we are using the like the assumption that we are doing OFDM and subcarrier or subspacing based, so it is constant. But if in 6G the design of the waveform changes, like maybe it goes to OTFS, then obviously we can look into that, how to allocate the power. The current consensus now for OTFS is not like it is challenging to extend it to multi-antenna systems. So we are also currently working on that to see if we can it can be done in multi-antenna systems. So in the future, maybe we can also look into how to allocate the power in that case, or whether it need to be significantly redesigned. So yeah, that's a good valid point. Thank you.
I think in your problems, as a solution, you are allocating the more power to those users having a rich channel state, having a rich channel situation from the signal to noise ratio point of view, because you are working in time domain.
Yeah, I mean, you can consider this as the frequency domain as well. So maybe this signal model here, let me just keep so here. So you can consider this as a subcarrier or subspacing based transmit signal. So at each subcarrier, there's a new precoder and there's a new data symbol, and the transmit signal is different. Or
Yes, similar to OFDM and waterfling.
yes,
Strategy.
definitely. And in that case, we don't consider like the waterfling scheme. We consider like an equal power allocation scheme because it is easy to consider in practice. But waterfling and maybe other types of power allocation in delayed Doppler domain could be considered to see if there is significant gain or how we can implement these to work in the next generation systems. That could also be investigated.
Thank you for your answer. And my final comment is that in such
sorry,
thank
Abid, may I interject?
sorry.
Because we are running past our time. If you have any conversation to have Onur, you can take it privately. I'm sorry, but we are already past half an hour, our allotted time. So
no problem.
thank
Okay,
you very
I will
much.
send you an email. Thank you.
Sure.
Yeah, sure.
Thank
Thank
you
you.
again for your presentation, and thank you for your organization.
Thank you.
Thank you for the questions and suggestions, Abid. Thank you, everybody, for joining in. We will share these slides on our website page. Please do look at the slides, and there we have the links as well. So thank you for joining in. And thank you, Onur, for giving such an engaging talk.
Thank you very much for participating and listening to me and inviting me to this seminar.
Thank you. Bye-bye.